about R0, or the basic reproduction number associated to certain systems of ODEs on Rn. And so I want to say a little bit first, very briefly, about R0, or basic reproduction numbers. So if you type it in Google, then you'll get something like this. I remember taking a picture of this maybe 2 or 3 years ago. So it's not as much about which links there are, but how many. So there's almost half a billion, or what is that? About 400 million links. And if you start reading them, even the Wikipedia page, it's not very revealing. At least it isn't to me. So, but yet there is quite a bit there, and at the same time, perhaps not enough, or not precise enough information. But nevertheless, it's a topic or a concept used quite frequently in population biology and epidemiology in particular. In population biology, you will see it more frequently in the context of discrete time models. Whereas in epidemiology, for some reason, you see it more frequently used in the context of differential equation models. And so this talk is more of the latter kind, and that's why the example I'll give is from epidemiology. So basic reproduction numbers are even common in popular press, or in newspapers, in news, in chats, and blogs, and you name it, and even in big Hollywood movies. So if you ever seen the movie Contagion 2011, it's a really star-studded cast there of A-list actors, and they talk about R0 as if it's their friend, so or at least an acquaintance. It's quite interesting to see that. Here's a typical example of a verbal definition. This is how I was exposed or heard about this the first time, maybe early 2000s, when I started working in math biology. And so the verbal definition in the context of infectious diseases goes a little bit like this. It's the expected number of secondary cases that are produced by a single typical infection in a completely susceptible population. I have to say that from experience, trying to use this verbal definition in a context of a precise mathematical model is usually a waste of time, okay? It can be done in simple models, but even then you have to be cautious not to make mistakes. It's very easy to make mistakes if you use this as an example. In fact, the very first paper I wrote, someone later pointed out to me that the definition I used was incorrect, or that the actual quantity I obtained was incorrect. And they were right, but for mathematical purposes, it didn't matter. And that was really what the point is of this talk. We will, instead of a verbal definition, we'll talk about a mathematical definition and look at some of its properties. And mathematically, the basic reproduction numbers are nothing more but spectral radii of linear operators. And the spectral radius of an operator is just the largest modulus of its eigenvalues, okay? So it's something that you can define precisely, and that is totally unambiguous. One of the problems, though, is that they're not uniquely defined. It depends on which operator you're actually considering, and there's a host of operators you can consider in this context, and that really confused me quite a long time. Okay, so a little bit of background. We need to talk about proper cones. So these are sets in Rn with the following properties. They have to be a cone, meaning convex set, which is invariant under non-negative scaling. So if you take a point and you multiply by any non-negative number, so you stretch it or you shrink it, then you're still in the cone, okay? It should be a closed set, and it should be a set with non-empty interior, okay? Sometimes you say solid here. And then finally, it has to be a pointed set, meaning that the intersection of the cone with its reflection with respect to the origin, so you take negative c as the set of all vectors negative x, where x is in C, well, that intersection is just the zero vector, nothing else. For example, a half plane in the plane, everything above the x-axis and including the x-axis, would not be a proper cone because it fails only this last condition. The intersection of half plane, upper and lower half plane is the entire line. That's not just the origin. Okay, some examples. So the basic example is the non-negative orthant cone, Rn plus. So these are the vectors with non-negative entries everywhere. But any orthant cone would do. So these are four sets of the following form: -1 to the gamma I xi is non-negative, and the gamma i's, there's n of them, are all fixed numbers in the set 0, 1. So it's either 0 or 1. If it's 0, your component is non-negative. If it's 1, it's non-positive. Then there's the Lorentz cone, or the ice cream cone. I'll give a little picture in R3 in a moment. It looks exactly like an ice cream cone. And then there's a slightly more abstract cone, if you want, of not in Rn, but in Rn squared, which we can think of as the n by n matrices in Rn. And if you look at those that are symmetric and positive semi-definite, right? So positive semi-definite means their eigenvalues are all non-negative real numbers. For an example, there's other definitions. That forms a cone, a proper cone, in fact. Okay. So the first set of cones here was what we call polyhedral, meaning you can write them as the finite intersection of half spaces. Okay, the positive orthant cone. And R2 is just intersection of two half spaces, everything to the right of the y-axis, everything above the x-axis. And these are then finitely generated by the identity vectors, right? So there's finitely many vectors with the property that any non-negative convex, non-negative combinations of these vectors generate the entire cone. The last two are not polyhedral. So for the ice cream cone, you'll see that quickly. You can't, and as a consequence, you cannot find finitely many generators. You need infinitely many ones. Here's a picture of the or a drawing of the ice cream cone. Okay, so it's a solid object. It's not just the boundary of this object. It's actually the solid thing, right? Okay, so another notion we need is the dual cone. So if I give you a cone, associated to it is a dual cone, which we denote by C star. And the dual cone is actually a set of linear functionals on Rn. So L in Rn star means that L is actually a linear functional on the set Rn. But not just any linear functional, it's those that are non-negative everywhere in the cone. So if you evaluate the linear functional in any point of the cone, you should get a non-negative quantity. And now Riesz representation theorem allows us to represent linear functionals as inner products. This is perhaps funny notation, but this is simply the dot product of y and x. Okay, so what we're saying is, since Riesz representation theorem allows us to represent linear functionals as inner products with vectors, we can identify the dual cones in Rn by actually subsets of Rn itself, such that the inner product of these vectors with anything in the cone is not negative. And it's a fact that dual cones are proper cones. Not immediately obvious, but it can be proved. And then all the examples I gave you, so the orthant cones, the Lorentz cone, and the cone of symmetric positive semi-definite matrices, all of these are self-dual, meaning they coincide with, the cone coincides with the dual cone. Okay, the dual cone of the positive orthant is the positive orthant, for instance. Okay, so now that we know what cones is, these nice geometrical objects that are quite general in a way, although we work quite often with positive orthant cone, we can ask the following question. If I give you a proper cone, and now I consider a differential equation x dot is ax, so A is going to be a linear operator here, or an n by n matrix if you want on Rn. What A's have the property that any solution starting in the cone remains in it? We'd like to know, one is the cone of forward invariant set. for a differential equation. And so another way of phrasing this is because the solution of a differential equation can be computed by matrix exponentials, right? So you get a semigroup in that way of n by n matrices, right? You can multiply them together and get a new exponential, right? That's why it's a semigroup. Of course, the identity is in it. When t equals 0, you get the identity here. Well, one else is this semigroup, this collection of n by n matrices. When does it have the property that it maps the cone into itself for all non-negative times? That's a different phrasing of the same question I posed above here. And in 1970, Schneider and Vidyasagar actually already answered this question. Okay, before we can answer it, we need to introduce one more concept. And that is the notion of a cross-positive operator on a cone. So suppose someone gives you a cone, ice cream cone or anything else, and then we will say that a linear operator is cross-positive on that cone if the following holds. If I give you a pair of vectors and dual vectors, so an x and a y, x being in the cone and y being in the dual cone. So here I don't necessarily demand that the dual cone is the same as the cone, okay? It was the case for all our examples, but it doesn't have to be the case in general. And if that pair satisfied their orthogonal, okay, their inner product is 0, so they're orthogonal vectors, then that dual vector has to have a dot product with a times x. So x was the vector in the cone, ax is some vector in Rn. Well, that inner product has to be non-negative. Okay. It takes time to digest this and to think about what should happen for operators and think through examples, but it's a very concise definition. That's what is nice about it. Okay, so here's the answer to the question I phrased. It's a theorem by Schneider and Vidyasagar. If you have a proper cone and some linear operator, then the cone is invariant for the differential equation, or equivalently this condition, right? The semigroup leaves invariant the cone if and only if the linear operator is a cross-positive matrix or linear operator, I should say, on the cone C, if this condition holds. So it's a characterization of all the linear operators A whose semigroup preserves the cone. So as an example, all you have to do is now, of course, find one is a given linear operator cross-positive. So you have to check this. For example, if the cone is Rn plus, the standard non-negative cone, it turns out that the matrix is cross-positive if and only if its off-diagonal entries are all non-negative. I don't care about the sign of the diagonal entries. It's the off-diagonal ones that all have to be non-negative. Okay, so it looks like very busy, but it's just standard notation for anyone's taken some linear algebra class. So I'm going to fix an operator on Rn, linear operator. Doesn't have to be cross-positive or anything, just standard notation of the following quantities. So the first thing is what we call the resolvent set of an operator, resolvent set of A. It's a set of complex numbers so that this inverse matrix exists. Okay, so lambda I minus A, I is the identity operator, of course, lambda is that complex number. If that difference has an inverse, then we declare lambda to be in the resolvent set of the operator A. This we often call the resolvent operator at the point lambda and associated to the operator A. This is the resolvent operator. This is the resolvent set. That's a set of complex numbers. The spectrum of A is just a complement in the complex numbers of the resolvent. And of course, in finite dimensions, which we're working in, that means we get the spectrum of the, we get the set of eigenvalues of the matrix A, and we call that more generally the spectrum of the matrix. Okay, so sigma of A is just a set of all eigenvalues of A, or the spectrum of A. And then two quantities associated to that spectrum are the spectral abscissa on the one hand and the spectral radius. Okay, the spectral abscissa is just the largest real part of over all the eigenvalues. So this the matrix A or operator A has n at most n distinct eigenvalues in the complex numbers. And you look at their real part, well, I'll take the largest one, that's the spectral abscissa. If you take, instead of the real parts, you take the modulus, you get the spectral radius. Okay. So here's an application of cross-positive matrices, also from the same paper by Schneider and Vidyasagar. It's an extension of the Perron-Frobenius theory, actually, or theorem. So if I take a cross-positive matrix, remember I characterized what those are. I gave a definition and proved something on. I didn't prove anything. Schneider Vidyasagar did it. But those are the special matrices right here, or operators here. Well, then their spectral abscissa turns out to be in the spectrum. Okay, that's not the case for any arbitrary matrix. Take the matrix 0, 1, negative 1, 0, that has eigenvalues plus minus I. So the spectral abscissa will be 0. That's the maximal, that's the largest real part of over the eigenvalues. The real part of both is 0. So, but it's not an 0 is not an eigenvalue of that matrix. Okay, so this is not an obvious statement. And moreover, not only is the spectral abscissa in the spectrum of the matrix, there's an eigenvector associated to it that can be chosen to be in the cone. Okay, so this is really an extension of Perron-Frobenius result that says for an operator that preserves a cone, not one that is cross-positive, but one that preserves the cone, meaning if you take the cone and map it by the operator, you back in the cone. Well, then the spectral radius of that operator is an eigenvalue, and there's an eigenvector associated to it that can be chosen in the cone. This generalizes that standard, or well-known, not standard, but well-known Perron-Frobenius theorem. Okay, so was there a question? Yeah, I'm sorry, I can only see my own screen, so it's a little, when I'm in full mode. Here's another characterization of cone-preserving semigroups. Oops, that's not what I want. Okay, hang on. Okay. Right. So there's a third concept here, that of a resolvent-positive operator. So again, I start with a cone in Rn. I take any linear operator, okay, and I'm going to define it to be a resolvent-positive operator on the cone if two conditions hold. The first one says there is some half ray in the complex plane that's actually on the real axis. So there's some alpha real number, and now I look at alpha up to infinity. So that's a half. No, that's not a half ray. That's a ray. It's a half line or a ray. Well, that ray should be part of the resolvent set. So in other words, that ray does not contain any eigenvalues of the operator A. This is actually always true for any operator A. In the finite dimensional case, which we're dealing with, this condition is actually always satisfied. It's the second part that explains why we call these resolvent operators, resolvent-positive operators. The resolvent preserves the cone, is what we're saying when we take the lambdas on that ray. So now you know that these lambdas belong to the resolvent set, so I can evaluate the resolvent operator, lambda I minus A inverse. Those operators map the cone into itself. Okay, that's what a resolvent-positive operator is. Okay, so here's a theorem. Take a proper cone and an arbitrary linear operator. Then an operator, that operator is resolvent-positive if and only if it's cross-positive on the cone. So that's a second. This resolvent-positiveness is a second characterization of generators or operators that generate a semigroup that leaves a cone invariant. Okay, because this first condition was equivalent to that. All right, and the various perspectives are useful at times, so that's why I'm reviewing this. You can find this in a result by Thieme in 1998, but this is not. I mean, he did it even more generally than in RN, but you can find this traces back way longer in time. I just didn't have the patience to find where. Certainly Arendt, who's being mentioned by Thieme, so you can start there if you want to do that. Okay. I'm just going to present the proof sketch. We do have a little bit of time, I guess. Well, maybe not. Well, let's see. Let's see how it goes. So we want to show, this is just a copy of the statement before. We want to show that an operator is resolvent-positive if and only if it's cross-positive. Okay. So let's prove cross-positiveness implies resolvent-positiveness first. So we want to show basically this second condition. Okay. Well, first of all, the ray, we can take SA to infinity. SA is the spectral abscissa of A. So to the right of SA are no eigenvalues. That's for sure. So that's going to be in the resolvent of A. That's good. And then here's a very nice formula. This says the resolvent operator for those lambdas on that ray is the Laplace transform of the semigroup e to the TA. That's what this says. This is a Laplace transform. Okay. And now if I hit a vector x, hit this resolvent with a vector x that belongs to the cone, then I can put it here in the integrand, but the matrix exponential keeps that vector x inside the cone for all positive times. And the exponential function here is a non-negative function. So I'm integrating something that brings me back into the cone for sure. So therefore the resolvent operator maps the cone into itself. So we've established this implication. The converse is a little bit harder. You would really need a relationship between the matrix exponential, the semigroup, and the resolvent operator, but backwards. So that would be like an inverse Laplace transform. And I'm sure one can do it, but I tried to avoid it. And I found a nice little formula here. So this says that the matrix exponent, this is a way to compute the solution of a differential equation in a elaborate way, but it's kind of nice if you look at it. It's a limit of a composition n times of resolvent operators right here that are scaled by these factors. And n over t goes, since n goes to infinity and t is assumed to be positive, n over t is a scalar, is a positive scalar that grows really big, right? So eventually it's going to be on this ray. That's the key thing. And so that means this resolvent makes sense and it preserves the cone because now we're assuming a resolvent operator. Okay. And so that means if I take a composition of such maps n times and then the limit exists, then since this formula is valid, then obviously this quantity will also be in the cone because this preserves the cone for each fixed n. And if the limit exists, then of course the limit must be in the cone because the cone is a closed set. Okay. So that means this is also in the cone. And that tells me that we have a cross-positive matrix. Okay. This is the main result. We're now ready to talk about the basic reproduction number. There's no typo here. There's a bold-faced S. And as you see, it says basic reproduction numbers more than one, okay? Plural, not singular. Are not is not a uniquely defined property. That's one of the messages I hope to get across. And it is the reason to create a lot of confusion in the literature, in my opinion. Okay, so we start with a cross-positive operator on the cone. So that means we know that the semigroup that it generates preserves the cone, or in other words, the cone is a forward invariant set. And what we're going to do is split that operator. Okay, and it may seem questionable if I can actually do that, but we'll return to that issue. for now, just try to follow along. So I'm going to write it as a sum of two things. And as from the start, what I'm doing is somewhat different from what you see in the literature, where it's written as the difference of two things. I prefer to write it as a sum, okay? But all I'm saying is, if you've seen it before, my formulas may look a little different and may confuse you at first. Okay, so what do I want about these two parts? Well, each of them is an operator on Rn, of course, but I want both to have the following properties. The first one says that F, the first term, must preserve the cone itself, so it maps the cone into itself. The second term has to be cross-positive, just like A is. It also has to, I demand it's cross-positive. But not only that, I also demand that its spectral abscissa is negative. Remember, spectral abscissa is the largest real part of the eigenvalues. Saying that that's negative means that all the eigenvalues of V have negative real part. So it's a stable or a Horowitz matrix, and control circles is what people call this. Okay, so if we can do this type of splitting, if we can find two terms that add to A and that have these properties, we call the splitting of A admissible. And now I can define the basic reproduction number for that splitting. It's the spectral radius of the composition of these operators, F and negative V inverse. Looks a little awkward, but okay, I told you what the spectral radius was, right? It's the largest modulus of all the eigenvalues of whatever this is. But this is an operator. In fact, I'll mark here that this is an operator that is preserving the cone. So if I apply this composition to any vector in the cone, I'm back in the cone. How do we know this? Well, here's the remark that explains it. So V is cross-positive by assumption, and its spectral abscissa is negative. But by the previous characterization, that means V is resolvent-positive. And 0 is in the resolvent set, right? 0 is to the right of SV, so it's going to be in the resolvent set. But that means this operator, R0V, exists. That's the inverse of 0 times I minus V inverse, that's negative V inverse. And since V is resolvent positive, that means that operator maps the cone into itself. So each of these two terms, now I recall that F itself maps the cone into itself. The composition of this composition is a composition of two maps which map the cone into itself. So their composition, the whole thing, maps the cone into itself. Okay? And R0 is nothing but the spectral radius of such a map, of a cone-preserving map. In fact, it turns out that this map has exactly R0 as an eigenvalue because of Perron-Frobenius theory that is extendable to cone-preserving maps. But we don't really need to know that at this stage. Okay, so this is how I defined my spectral radius. But as you notice, it all hinges on the assumption that we can split our operator. Can we? Do admissible splittings of A always exist? Well, my claim is yeah. Here's the answer. So we take a cross-positive operator on a cone, and we're going to split it in a very funny way. So the first term is T times the identity. The second term is A, the constant matrix, minus T times the identity. If I add this, of course, I get A. And I'm going to assume T is bigger than 0 and bigger than S, the spectral abscissa of A. Well, in that case, the R0 becomes dependent on the little parameter T, right? There's many T's allowable here. And but by definition, given before, it's the spectral radius of Ft times the inverse of negative V. And I claim that that's going to be the following expression of T. It's a rational function of T. Okay. All right. So here's a picture, by the way, of R0 of T. Okay. In three distinct cases. If SA is negative, of course, the maximum of these two is 0. If SA is 0, the maximum of these two is 0. And if SA is positive, the maximum is actually equal to SA. So I have these three distinct cases. The domain for this expression depends on the sign of S of A. Okay, if S of A is negative, here's the plot of R naught of T, of this function. It's an increasing function from 0 to 1. If SA is 0, it's a constant function, right? If SA is 0, it's T over T, that's a constant 1 function. If SA is positive, it's a decreasing function of T to the right of S of A. Now, what is important to note is that what is the range of each case? Well, in this case, the range of my map R naught of T is the entire interval 0, 1. I can get any value between 0 and 1 for R naught of T. In the case SA is positive, I get the entire interval from 1 to infinity is in the range. Okay, so I know there's always a splitting whose corresponding R naught takes any value between 1 and infinity. Okay, but let me just prove. Actually, I'm not going to sketch the proof. I don't. It's not difficult. The main thing is to check this formula, but that comes from the spectral mapping theorem of linear algebra functional analysis. It's an immediate application. It's not difficult. Okay, so here is a very important theorem. This is why basic reproduction numbers are so ubiquitous in epidemiology and ecology. They basically relate the location of the spectral abscissa of the operator A to their own value. So let me say that again. If you're interested in knowing the spectral abscissa of some matrix A, the reason you want to know what it is because you want to study the stability of a steady state, typically. And the sign of S of A tells you whether you have a stable or unstable steady state. But in many cases, finding this spectral abscissa is too difficult. You can't compute it. The theorem here tells us R naught is a good proxy. It's a way to get a sense of where the SA is located without having to calculate SA. And the advantage, surprisingly, is that it's often easier to calculate basic reproduction numbers than it is to calculate directly the spectral abscissa. Okay, so what's the theorem? Well, we take a cross-positive operator on a proper cone, we split it in an admissible way, and we define R naught to be the spectral radius. Then the spectral abscissa is negative if and only if R naught is less than 1. S of A is 0 if and only if R naught equals 1. And S of A is positive if and only if R naught is strictly bigger than 1. Okay, so it's a trichotomy. Exactly one of these three cases occurs. So the value of R naught depends on how we split A, right? And I showed you that there's many ways to do it. Trivially so in a certain sense. For example, we saw that if SA was positive, then we can always find a splitting such that the R naught value is anything in 1 infinity. That was this third picture here, this picture. If SA is positive, which it is in this case, then we can find we always can find a splitting that assigns any value bigger than 1 to R naught. Okay? Okay. So any biological interpretation of R naught has to proceed with caution. You can't just talk about the absolute value of R naught, which is what unfortunately often is done in biological talks. People compare numbers of R naught in order to give a sense of the infectiousness of a disease, for example. Perhaps they want to rank diseases. But if you don't tell me how you split your operator to begin with or what your operator was, this is meaningless. Because I could always split it in a different way, possibly, and get a quite different value. That's the whole point. Okay. And it gets even worse if you have the infectious diseases that are very different, that have different compartments of people that are infected and latently infected, and maybe the disease is wanes, or maybe you're always having it. it leads to different models. And then those models have different matrices A in the end, and how to compare the value for one type of matrix, which may be of a size 100 times 100, and one that's of size 5 by 5. I don't know how you can make meaningful comparisons. And then things get even worse beyond that, because what is often done is one wants to control R naught. Okay, and initially the reason to do so is clear. It's this theorem. Say if R naught is bigger than 1, that corresponds to some matrix, typically a disease-free steady state linearization matrix, being unstable. Okay, well, you want to control the disease, you want to make it stable, so you want to make S of A negative. Well, that means I need to decrease R naught from something bigger to 1 to something less than 1. Okay, and so that's the typical strategy in disease control. Try to lower R naught from above 1 to below 1. Okay. Now, here's a question I want to raise. What if you know that your control efforts fail? Despite your best attempts, it simply isn't possible to decrease R naught to something less than 1. And that's not just a vacuous question or irrelevant question, because I claim for any endemic infectious disease that's around, this is the case. Despite all our best efforts, the disease is still around, so we haven't stabilized the disease-free steady state. Okay, well, in that case, you may be decreasing R naught, your control efforts actually might be decreasing R naught, but at the same time they're it is possible, not always, that you're increasing S of A, the spectral abscissa of the operator that really matters. So you're making things worse, is what I'm saying here. It's possible you're making things worse by focusing only on decreasing R naught. Okay, just to illustrate, and that will wrap it up here, a simple, very basic infectious disease model with some demography, meaning you have some births in there. So this is a susceptible equation, differential equation. This is the infected differential equation. There could be a recovered class, but I'm not modeling it. It's irrelevant for what I want to tell you. Okay, so you have 4 parameters, K, alpha, beta, and gamma. These are all positive constants for now. There's a mass action term to describe infection. Okay, so there's a loss of susceptibles due to infection. Infection is proportional with the numbers of susceptibles and infected. And then they show up as in the infected class here. And then alpha and gamma are the death rates of the susceptibles, say, and the infectives. Often there's a relationship. Maybe gamma is bigger than alpha. This is the sick people, right? So the death rate might be higher than alpha. And then there's births right here. Beta is the birth rate. Okay. So this has a disease-free steady state. So there's a steady state. S is beta alpha. I is 0, which corresponds to no disease. And if you linearize, we get an operator of this type. Okay. And this is not an operator that's cross-positive on the regular orthant cone, but it is cross-positive. This is a little exercise. You just believe me. On the second quadrant in the R2. So the X1 is negative. So X is negative and the Y variable is positive. That's the second quadrant or orthant in R2. Okay. So we can split now my operator in 2 parts. So I'm taking only this piece and I put that here in the first matrix F. And all the other stuff, the negative stuff here, is arranged in the matrix V right there. And I claim that's an admissible splitting. So first of all, I have to check, is F preserving the second quadrant? And yes, if you do a little exercise, you can convince yourself, take any vector in the second quadrant, apply this matrix, your resulting vector is still in the quadrant, second quadrant. V, the second matrix, is cross-positive. That's also a little exercise, but we have a criterion. I gave it very early on in the talk. And then secondly, what is the spectral abscissa? Well, it's a triangular matrix. So I can read off the eigenvalues on the diagonal. It's negative alpha, negative gamma. The biggest of these two, the rightmost value is the spectral abscissa of V. And that's, of course, negative. Okay. So now I define R naught in the usual way, in the recipe I gave you. It's K beta over alpha gamma. And SA, that's a separate calculation. Here it can be done because of the low dimensionality. It's just a maximum of these two, low dimensionality and the fact that this is triangular matrix. So here you see directly the trichotomy illustrated. This is less than 1, this ratio is less than 1, if and only if SA is negative, okay? Meaning if this quantity is negative, that's equivalent to this being less than 1. Being bigger than 1 is equivalent to this being bigger than 1. And equal to 1 means this equals 1. Okay. And that illustrates just the trichotomy quite well. Okay, so here I'm going to think of an abstract control scenario, one that's inadvertent, but one that I think people often don't think about. So often you want to perform a control and lower or increase some control, some parameter in a model. And without thinking, it may affect other parameters in the model. And the combined effect can lead to something really dangerous. That's really what I'm trying to outline here. Okay, it is that, so it's the idea, what is the effect of my control parameter, not just on the thing that I'm interested in decreasing or increasing, but also what's perhaps an unintended effect on other parameters in the model. Okay, so just abstractly, the death rate of the susceptibles, which was the alpha, I make that a function of a variable u, control variable. Let's say that's decreasing. I'm going to keep the birth rate of susceptibles constant to beta. Gamma, I'm going to have increased, that's the death rate of infected people. And K is the infection rate is supposed to increase. Okay. How do I do this? So think of what happened in the 20th century. Our medical system went so much better. Healthcare, medicine developed and so on. But it resulted in an aging population. Okay. And so the death rate of susceptibles may have decreased because we live longer, more productive lives. The infection rates and the death rates of infected people could have increased. And why? We have more older people, they're more vulnerable to disease. So they're more easily infected, for example, by their grandkids. And they die quicker because, yeah, they're more susceptible to the adverse effects of a disease combined with old age. Okay. So the common cold would be a typical example. We're not getting rid of it. It's still around and it wreaks havoc. So let's say before control, U is U naught. So this is like a baseline before control. And we assume that before control, our model has the property that there's an infection. So it's an unstable disease-free steady state. S is positive and R naught by the trichotomy is bigger than 1. Okay, so I claim that it is possible that if I'm unlucky with my parameters, control parameters that are functions with the properties on the previous slide, that the following happens. I decrease R naught, which is the usual thing people do in epidemiology, but I'm actually increasing the spectral abscissa. Okay. Just a one-page proof, okay? This is it. So this is just a repetition. There exist betas, alpha decreasing, gamma and K increasing, so that these two properties hold. So with I gave you expressions of R naught and of S of A. Using those expressions and now making the parameters depend on U, I can show that this requirement, this being negative, this being positive, amounts to these two inequalities. And the red thing here, let's call that A, that's a derivative of gamma. Gamma was the death rate of infectives. That same derivative appears here, but it's multiplied by R naught at U naught. Okay, so this number is bigger than that number, and both are positive because gamma is increasing. So we create an interval AB of positive numbers. Okay, so all I need is to say, can I find functions or a constant beta and functions K and alpha, so that the derivative of that ratio times beta is in that interval AB. And of course, K and alpha have certain properties, but they imply that that ratio is increasing. So this is going to be a positive quantity for all K and alpha increasing. If I multiply this by a beta, a smartly chosen beta, I can make it happen that resulting number is in the given interval AB. Okay, and so what happens then is I get the opposite effect from what I intended. R naught is decreasing. I think I'm doing a good job, but S is increasing. The disease gets more infectious in some ways because you're destabilizing more.